When discussing chemical rates and chemical kinetics, we have said that molecules need to collide, and the faster molecules move, the higher the chances that molecules collide with each other and reactants become products. Now, let's see if we can understand a little bit the relationship between temperature and speed of molecules that we may have in a sample. And this is applicable to gas. For liquids is a little bit different, but not that very different. So let's just talk in a very general terms, a whole area called the kinetic molecular theory that was developed at the end of the 19th century, that just assuming basic assumptions about the molecular nature of gases, it just shows us what is the distribution of velocities or speeds in a gas. In here you see this distribution at this temperature. Notice that as you increase the temperature, the peak moves to the right, but also that curve flattens a little bit. On the Y you see the relative number of molecules, and on the Y axis, on the X axis, what you see is the speed. And I'll let you think about a little bit how fast this is. This is 1 kilometer, so it's a little bit more than half a mile per second. So there are, even at room temperature, there are some molecules that move at 1 mile per second. This is pretty fast for molecules. Well, this is pretty fast for us, apparently not for molecules. But what it's clear that as you increase the temperature of that gas, the distribution gets wider. That is, the peak is less narrow and the average increases. This follows what's called the Maxwell-Boltzmann distribution, and if you cannot see the trend here, this function is pretty much something like that. Okay, if you plot in your favorite plotting program, you will see that this function really has a shape, a little bit shaped like that. Notice that the mass is here and here, so, and the temperature is also here and here. So you will see that both mass and temperature have a very similar and contradictory effect. This was the effect of temperature. Now let's see the effect of mass. What happens if we take a sample of different gases at the same temperature and we study the distribution of velocities? You will see that the lightest of the mass has a more flattened peak, but also a higher average. Okay, so followed by, so first the lightest of all these gases is hydrogen, followed by helium, water, nitrogen, and oxygen molecule. So in a way, you have to think that having the same temperature but lighter mass is as if we were increasing the temperature of that gas. Let me put it here in writing. We said if you have something like that, the higher the temperature, if you will, the higher the peak of this curve, and it'll be flatter. Okay, which has the same effect as for comparing the same temperature. The lower the mass, you will have the higher will be the peak of the speed, and the flatter the peak will be. Okay, let's just run a simple exercise to make sure that this makes some sense. In this case, we are given 4 possible gases: argon, chlorine, methane, and xenon, all of them at the same temperature. So the only effect that we are considering is mass, and it's asking us which gas is which in this representation. First of all, let's assess which one is the lightest. Methane is just 1 carbon and 4 hydrogens, is the lightest of all, followed by, careful here, argon is heavier than 1 molecule of chlorine, but if we're talking about chlorine gas, you'll have 2 chlorines, and finally the heaviest of all is xenon. The only trick in this problem was if you have not put the chlorine 2 in here, you would have said that chlorine gas was lighter than argon. But if we accept this trend, you will see that, well, the heavier you have your gas, the more narrow your peak will be. So this is xenon because it's the slowest of all gases, and it's the more narrow peak, followed by chlorine, followed by argon, and finally this is methane. Okay, this is the effect of mass on velocity of different samples of gases all at the same temperature. Now the question is, if all these graphs represented the same gas but at different temperatures, which one would represent, say, 50, 100, 150, and 200? We said that the smaller the temperature, the higher the peak and the more displaced to the left, that is the lower the average velocity. So this would be the 50 Kelvin, followed by the 100 Kelvin, followed by the 150 Kelvin, and followed by the 200 Kelvin. These expressions will just allow us to understand with a little bit more detail the relationship between temperature and speed of molecules. So now we know that in a sample of reactants, even if all of your reactants have the same temperature, the lightest of those reactants will be moving faster. Therefore, the likelihood of colliding and leading to products will be higher.